So before we move to today's main topic, I want to just briefly summarize what we did yesterday and present some further motivation for the tutorial you are going to do this afternoon, where we will also do some simple classical string computation. So yesterday we studied a rigid rotating string, okay? And let me summarize a bit how to describe this solution and remind you that yesterday, most of you were already here at yesterday afternoon when I corrected one statement where we said that we would use the equations of motion to fix the maximum size of this string as function of its angular velocity. Of course, that was nonsense, because as soon as we are describing an Ambu-Goto string, which is parameterization invariant, all I have to tell you is how does the string look like. The particular parameterization is irrelevant. So of course, studying equations of motion and dependence on sigma was pointless. All we have to say is that we have a rigid string, it rotates with some angular frequency, and it has some maximum size. Then a particular grid that you put to say where your spacing is totally irrelevant. The string is totally described by this cartoon, by this picture. Not cartoon, a precise picture. These endpoints move at the speed of light. This tells you what's the relation between omega and rho. So this string is uniquely described as soon as you say what is the angular frequency. And then the energy and the spin are computed respectively by integrating this or this over each half segment of the string, and you multiply by 4 because there are 4 such segments there. In particular, this gives you energy as function of the spin, and at large spin, it is proportional to the logarithm of the spin, which is a nice feature. It would immediately rule out AdS CFT if it was not the case, because we know that in any gauge theory, the dimension of operators at a very large spin should grow logarithmically with a spin. Okay? So at the time, this was an extremely important check of AdS CFT. This was 1 year after AdS CFT came about, and it was a nice check that it was indeed, for a very non-trivial string solution, giving the right dependence as we expect on general grounds for any gauge theory at any coupling. Okay, so it was a good indication that the way things were scaling with the spin was correct. Now this function, this cusp dimension, we just computed it in this way at strong coupling, can be computed at weak coupling to many loop orders, it can be computed at strong coupling as well. This was the classical computation we did. This would be summing quantum fluctuations around the solution. This would be doing a tough computation, and so on. So let me just make a few comments. I'll probably say them again tomorrow, but let me make a few comments about the feature of these expansions. First of all, let me emphasize that this constant here, for example, starting at this one and the later ones, these are quite hard to compute. Similarly here, at high loop order, they are very hard to compute, of course. And the point will be that we will be able to draw a curve indeed going all the way, because we will develop some very powerful techniques. And the techniques that will allow us to plot this curve are what goes by the name of integrability. Some exact solvability that is hidden somewhere and waiting to be discovered, and that's what we will do today, inside these remarkable theories, both n equals 4 and string theory. And in fact, using integrability, one comment I wrote here, the third one, is that the cusp dimension is now known exactly from integrability. You can really plot this function all the way from weak to strong coupling. And this is really something remarkable that would be unthinkable a few years ago. How could you ever plot something exactly in a gauge theory? And this I will show you the plot tomorrow. Actually, we will implement the plot in Mathematica. It takes a few lines. So we will plot this cusp anomalous dimension tomorrow at any value of the coupling. Okay, so this integrability approach allows us to compute this f of lambda. And actually, it was from integrability that this constant was computed correctly for the first time. There was a previous computation that was actually incorrect. They had a Catalan number plus other stuff. The integrability people computed using these techniques, and they saw only the Catalan number. And then people who did the perturbative computation found a mistake, they fixed, and indeed it was just a Catalan number. Similarly, at weak coupling, the number I wrote yesterday I wrote it yesterday, or 2 days ago. I wrote this number exactly at for loops, the for loop value for the cusp anomalous dimension, because it was computed from integrability. It was not computed by Feynman diagrams. Only numerically it was computed by Feynman diagrams. And people check that the number they get from numerics matches this complicated number that people got analytically from integrability. So the situation improved a bit. Yesterday night, people computed this number analytically. Okay? So there was a paper coming out this evening where people computed this number. This one, integrability, can immediately predict, and then it will take a few more years till people catch up. Very good. So what are we going to do in today's tutorial? Today's tutorial is about another important physical quantity. There are so many. Here we just chose one to illustrate the CFT. But another important physical quantity whenever you have a gauge theory is to study the potential between two particles. Do they interact? Do they attract? Do they repel? What's the interaction potential between two heavy charged particles? What's called the quark-antiquark potential. So if you have two heavy particles, you can think of them, if you want, as a quark and an antiquark. And they are separated by some distance r. You can ask, what is the potential V of r? Now, in any conformal field theory, in a CFT, because of dimensions and because you have no scale, it should be given by some function that could depend on the coupling divided by r. And I believe, but conventionally there is a minus, but I don't remember actually, so you'll see in the tutorial. Okay. And then what you might ask is, okay, how do I compute this potential? How to, one, compute V of r at strong coupling. And do two things. First of all, check the dependence with r. So that ought to come out correctly in the same way that here the dependence with the spin should come out correctly, and it did. So first, immediately see, is it indeed of the form something over the radius? Okay, that's the first thing. And second thing, how can we compute, once it's okay, we compute alpha of lambda at strong coupling. Now, at weak coupling, alpha of lambda, how do we compute an interaction between two particles? You just compute the exchange of a gluon between the two particles. And it is just Coulomb interaction, and it is just a one-loop diagram, and this alpha is just lambda over 2 pi squared. It actually is the same as the cusp dimension, just the typical number that comes out from one-loop computations. So what we will do is ask ourselves, how does the plot look like? Well, it will be a plot very similar to the one we drew there. It starts with lambda over 2 pi squared. Okay? And in the afternoon, you will see that it goes to some value at strong coupling, which is 4 pi squared, square root of lambda, over gamma to the 1/4 to the power 4 plus corrections. Okay? So this is what you are asked to do, to sketch this plot, to compute a strong coupling, to draw the line at weak coupling, and just draw some sketch like this. Of course, you could ask yourself, is it also possible to compute the full curve? And actually, the answer is yes and no. There are equations written that if you solve them, you can compute this curve exactly. They were computed last year. But people didn't solve them yet and plot them for some strange reason. So you are welcome to do it if you want. It's a nice project. Okay, very good. So this is the goal. So how does it work? What's the prescription for computing this? The prescription is the following. What you should do, the dictionary tells you that the potential V of r is given by the limit when t goes to infinity, 1 over t times square root lambda over 2 pi times the area of some minimal surface eta. It's actually not the area, because this area will be divergent, so it is some regularized area. Let me explain it in a minute, how do I have to regularize this expression. And what is this sigma? Well, it's the only thing it could be. You have the boundary of AdS. Now we are using Poincare coordinates. And this is AdS in Poincare coordinates. So you have z, and here in this plane you have Poincare coordinates x mu. And what you do is you consider an infinitely long rectangle or a very long rectangle. And you compute the area of the string, the minimal area of this tent, where this direction is much bigger than the separation is t, and this direction is r. Here. Okay. So this is the prescription for computing the quark-antiquark potential. Okay. Now, where does this prescription comes from? So this is the boundary at z equal to 0. So I have to explain you why does this need to be regularized, and where does this prescription come from. But I just want to motivate it briefly. I don't want to go into details, because this is a slight detour just to motivate the computation that you are going to do, which is very well posed. Just compute this minimal surface and compute the area and so on. The main goal of the tutorial is to give you some experience computing this, and I don't want to make a big detour towards the motivation of this subject. But just to see why it should be something like this. Because remember, in the original derivation, where was the stack of branes? The stack of branes was, okay, here, which is z equal infinity, not z equals 0. Remember, z equal infinity was r equals 0 first. Right? Because z is 1 over r. Then how do we put a very massive particle? Well, what we do is we take an open string and put a brane here, very far away, so at z equals 0, and stretch an open string between the two. This is how we create a very heavy particle. So a very heavy particle should be described by a contour at z equals 0, which is how we do it to make it very massive. And that's why we are putting some contour here, one contour for the quark and one contour for the antiquark, in the boundary of AdS. Okay, just a motivation. But notice that even if you would put just a single particle, you would just stretch even just a single particle here. You would just put it and stretch it until it goes all the way to z equal infinity. So it would just go up, and this would define some surface sigma naught. And this would be what you would do to describe just a bare particle without any interaction. A bare massive particle. And here is the other one, and you do nothing to it. But now, this is divergent because close to the boundary, these guys are divergent because close to the boundary, the metric goes like 1 over z squared. So it costs lots of area. This area here close to the boundary, it has a huge amount of area. But this is fine. This is just the self-energy of a particle that needs to be renormalized. The self-energy is divergent, and you need to subtract it. So it's clear what you should do. If this is the interacting case, and this is the free case, what you should do, but what this area regularized means, it means area of sigma minus the area of the empty guys, which is twice the area of these surfaces that just go up. Okay. But in practice, it's easy to see that in practice this is the same as doing the following. This is equivalent to writing that the area of sigma is equal to something over epsilon, where epsilon is a cutoff. You cut your surface, you only consider the surface above some epsilon. Okay, so you consider the surface above some epsilon. Then the area diverges with epsilon, and the finite part is the physical part. Okay? So you expand in epsilon, take the finite part, which is what should be your quark-antiquark potential. This is equivalent to doing the subtraction procedure I explained. Yes?
Maybe I'm associating the wrong things together, but I thought that in string theory we didn't have those infinite things you have to renormalize away. Or is that for some other context?
Here, what you are doing is making from string theory a prediction for the interaction between two quarks in the field theory, right? So they're hot a bit. So the divergences, you see, they are not ultraviolet divergences because of the string. They are infrared divergences from the point of view of the string, because the string has some huge area as it's approaching the boundary. In other words, as soon as you consider some finite piece of string, everything is finite. It's because you are considering a huge area of the string as it goes to infinity. And that is reproducing this infrared divergence of strings, that is perfectly okay to have, is reproducing the ultraviolet divergences due to mass normalization of the heavy quarks. Okay? But if you want, the quantity you compute is this quantity minus this quantity. This is totally finite. Okay? Okay, very good. I could give you a few more details, but maybe, let's see. If I have time at the very end, I come and give you a few more comments. Otherwise, basically what you will be asked to do is study this surface, again with Nambu-Goto. Study its shape. Remember again, don't do the mistake I did yesterday. All it matters is the shape of the surface. Parameterization is independent, so all you care is what's the shape of the surface. So you can use some nice parameterization where this is sigma, if you want, and this is tau, and you parameterize everything in terms of the plane here, and you will see in the exercise. And you will find indeed that the potential is as it should be of Coulomb form, and that this is the coefficient of the potential. Okay. Okay, so I now move to the main part, to the main topic that I want to discuss, which is to try to find some hope of ever computing this curve exactly, and we will re-examine the weak coupling computation. We already computed it twice. We will compute it a third time, or see how we would compute it a third time. Maybe not finish the computation all the way. So we will go back to spin chains. Okay, where I remind you, we have some Hamiltonian, our mixing matrix, which is a sum of some one loop Hamiltonians, density, plus at higher loop longer range interaction. And this guy acts on operators, OS, given by And how does the Hamiltonian act? Well, it can hop the derivative from one place to the other. And we have to diagonalize this Hamiltonian. Now, let me just remind you, I should have written this before the lecture starts, but I forgot. So let me just write here the most relevant interactions that we need when we will study a small number of derivatives. So I'm going to study 0 derivatives, 1 derivative, or 2 derivatives, and then tell you the result for 3 derivatives. So the Hamiltonian preserves the number of derivatives, it just moves them around. So all I need to write is what's the Hamiltonian acting on 0, 0. What's the Hamiltonian density acting on 1, 0? What's the Hamiltonian density acting on 0, 1? What's the Hamiltonian density acting on 2, 0? What's the Hamiltonian density acting on 0, 2? And what is the Hamiltonian density acting on 1, 1? Okay, so this is all I have to do. Up to 2 derivatives, this is all we need. And you computed this in your tutorial, right? So let me just copy it here. Okay. Very good. Now, it's important if you now ask me if you have any question about this pinch change story. Otherwise, you will be lost for the full, until the more or less the end of tomorrow. So, is it clear? Yeah? Even if you don't know very well how to phrase what is unclear, it's better if you speak out now. No? It's okay? Very good. So we are going to now consider this pinch chain approach from this point of view that we start with a vacuum. Okay? So we have a vacuum, which is just the state which has no derivatives at all. Just Z fields. And let's take the number of Z fields to be, not very small. It can be bigger than, whatever it is. It can be big if you want. It is often convenient to think that this is big, but it's not important. Okay, there is L fields, okay? And let's keep in our mind that L is somehow big, even though it's not important, but it's useful. And then what we consider is, this is the vacuum, and now we have states which have one particle. So by one particle, it means that you have nothing, and then at some position n, you have a derivative, and then nothing. Okay? But of course, this is not an eigenvector, because when I act with my dilatation operator, the derivative moves. So this, of course, is not an eigenvector of my Hamiltonian. So how do I construct an eigenvector? I multiply this by a wave function psi of n, and I sum over n from 1 all the way to L, wherever it moves. Okay? And we denote this by the cat n. Okay? Then, if you impose that gamma acting on, this Hamiltonian density should contain some lambda. So all this times lambda over 8 pi squared, right? All this as an overall lambda over 8 pi squared multiplying it. So gamma acting on our cat psi equal energy times psi. Let's see what does it give us. Okay. So the picture is that we have here some wave function psi that describes the vacuum, and then there is some derivative somewhere. I don't write the other guys, they are just empty. And we are going to put this derivative moving with some momentum along this vacuum. So this equation there for the wave function becomes, well, you compare now different components of this wave function, and you get that energy times psi of n equal to lambda over 8 pi squared. And now let's see. Whenever the Hamiltonian acts here, 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 it does nothing. Only when the Hamiltonian acts close to the derivative, only when the Hamiltonian acts either here or here, it gives something non-zero, and it hops the derivative from the previous guy or from the next guy. So in position space, the Hamiltonian becomes, so when it acts here and here, there are two terms where it does nothing. This one, when it does nothing, and this one, and the first one, and the first one on the first line. So there is twice psi of n minus psi of n plus 1 minus psi of n minus 1. Okay? So this is just position space Schrodinger equation. Again, please tell me if I'm going too fast at some point or if I'm going too slow. So this, of course, is diagonalized by a plane wave, as any translational invariant system is. So this is diagonalized if we write psi of n is equal to e to the IPN, which is the same as giving the particle a momentum. And in that case, we conclude that the energy, which depends on p, is equal to lambda over 8 pi squared 2 minus e to the IP minus e to the minus IP. Is it clear? Just plugging wave function and dividing by e to the IPN. So this is equal to lambda over 4 pi square 1 minus cosine p, which is lambda over 2 pi square sine square of p over 2. Okay, very good. So this is epsilon of p. Epsilon of p, the energy of an excitation, has energy lambda over 2 pi square sine square of p over 2 plus dot dot dot, where dot 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 will be from higher loop corrections. Okay, plus order lambda square. Okay. So there's nothing else to say about a single particle moving in a vacuum. This is all there is to say. Nothing else. So now we move to the next case, which is two particles. Two particles are more interesting because they can start interacting with each other. Okay, very good. So we take two particles and we write a wave function psi, which would be what? It would be sum. There will be some wave function psi that depends on n1 and n2. And then we can have n1, n2, okay, where this means that there is a derivative at position n1 and n2. Okay? For example, 1, 5 means in the first z and on the fifth z there is a derivative. 3, 3 means that on the third z there are two derivatives on top of each other. It's clear? And we don't want to overcount, so we sum over n1, say smaller or equal to n2. This covers all the Hilbert space. Okay, so how does Schrödinger equation look like for the two particle case? Well, it's easy. Now you act with Hamiltonian and compare components. So you get that energy times psi of n1, n2 is equal, okay? So this describes, again, some derivative and some derivative at position n2 and at position n1. Okay? And again, they can come from the neighbors. So there is twice. If we focus on the first guy, n1, n2 minus psi, n1 plus 1, n2 minus psi, n1 minus 1, n2. And if we look at the second guy, the same thing where we shift the second guy. And I forgot lambda over 8 pi squared, so let me put it here. Okay? This is clear, right? But now notice that this is okay if they are separated. So this is if n1 is smaller than n2. Okay? So this tells you that particles, if they are not on top of each other, they are just moving. They don't know about each other. It is just Laplacian on first particle, Laplacian on the second particle. Discrete Laplacian on first particle, discrete Laplacian on the second particle. But if they are close to each other, we have to be more careful and use now the Hamiltonian coming from these last lines. Okay? So we have this equation, but we have another one when they are close, which tells us that 8 pi squared over lambda times energy times psi of n1, n1. Okay, so this is what we get for n2 equal to n1. Okay. So what can it be? Okay. So what will it be? It will be the following. Let's write okay, let me write the result and then comment on where it comes from. So there are these terms where we act on the position that they are already on top of each other. So I remind you that this means two derivatives at position n1. So this means that you have at position n1 you have two derivatives, this square. So there is one case where the Hamiltonian acts there and there where it just takes the identity. So there is 3/2 psi n1 n1 minus psi n1 minus 1 n1 minus 1/2 of psi n1 minus 1 n1 minus 1, and then plus the same thing when you think about the other guy, n1 n1 minus psi n1 n1 plus 1 minus 1/2 psi n1 plus 1 n1 plus 1. Okay, so let's again see. So, okay, so first of all, you agree that what I'm telling you is, I mean, conceptually it's very clear. We are just acting with Hamiltonian and collecting coefficients, right? So I'm just trying to make it even more clear by just explaining where the terms come from. But you are free to just ignore and redo it yourself in whatever way you want. So, but let's try to see where they come from. So let's put here A, just B, C, D, E, and F. Okay. So who can give, after acting with H, who can give a configuration where they are on top of each other, right? So which wave functions could contribute such that after acting they give a ket where they are on top of each other? So what we have to do is look on the right-hand side and see where is there a 2, 0. And there is one here, another here, another here, another here, another here, and another here. So you see that there are 6 terms here which can indeed produce two derivatives on top of each other. And how many terms are there? 6. Okay? So it's really a one-to-one correspondence. So we can say that A can come, for example, from this term. B comes from D comes from this term, say. Then how can you get what happened here? Here you had one derivative here and one here, and this derivative hopped there. So it was when you had 1, 1, you had 1, 1, and the derivative hopped to the right. So this is B. When you add 1, 1 and the derivative hops to the left, it's this case. It's when you add this one here. No, sorry, it's C. And here is when you add 1, 1, and then it humps to the other direction. So that's F. So this is C, and this is F. Okay? And no, sorry, I apologize. Sorry. Okay, so let me start again. So these ones are clear, right? Now, what about B? B, indeed, you have one particle and one particle close to it. And here, E, you have one particle and one particle close to it, not on top of each other. So these two guys are the one that came from 1, 1. And this guy came by moving to the right, and this guy came by moving to the left. So both come from 1, 1, but one moving to the right, one to the left. So the one where the guy moves to the left is the second one. So this is E, and this is where it moves to the right, it's B. The last two here, they are also on top of each other. This is also a state with two derivatives on top of each other. But here it's to the left of where we are, and here it's to the right of where we are. So it's the case where the two derivatives hop together. And in one case, they hop to the right. So that's the first line. So this would be B. And here, they hop to the left. So this would be F. Okay? Again, I'm explaining something that you can, of course, just do it by yourselves if you want. Okay, very good. So how do we propose now to solve these equations? Any proposal? Okay, one particle we did. It was psi for one particle. We had psi of n equal e to the I n p. So a proposal. What do you propose to do for n1, n2? No, you don't want to prove. Yeah.
Product state?
Sorry?
Product state? I mean, the
Two plane waves. That's what you mean?
multiplying those together. So N1 P1 plus N2 P2.
Okay, very good. Let's see. So, as you are saying, we can put now a particle P1 N1 plus I P2 N2. Okay, this is a good attempt. But maybe this is not enough, because what we expect in general in one dimension, we have particles with momentum P1 and P2, and they conserve momentum and energy, but they can scatter, right? So the momenta, because they conserve momentum and energy, in one dimension, what happens when you have two balls colliding with the same mass? They can at most exchange the momenta or do nothing, but they can exchange the momenta. So just this term by itself should not be sufficient. You should also allow for the possibility of exchanging the momenta, P2 and 1 plus I, P1 and 2. And the relative coefficient between the two, we call it S, some number, okay? So you can think that this is like some ingoing and this is like some outgoing wave, okay? And this would be the most general thing you would write. So this ansatz follows, again, from the existence of two conserved charges, one which we can call Q1, which is just the sum of the momenta, and the other one which we call Q2, which is the sum of the energies of the particle. So if energies and momentums are conserved, if you have two momenta, you can exchange them, of course. You can just permute them, but nothing else for two particles. Now, indeed, just a plane wave by itself would solve perfectly well this equation, because this equation is just free, it doesn't know about the other particle. So both this term and this term, both independently, they diagonalize perfectly the first equation. And therefore, from the first equation, we read off immediately that the energy is nothing but epsilon of P1 plus epsilon of P2. That is, the energy of the two particles is given by the sum of the energies of each particle, where epsilon of P is given in this box here. Okay? So this is just from considered reading off the energy from the region where particles are very separated. But if you plug into this equation, it is no longer true that for any linear combination of plane waves, this equation is satisfied. So this equation fixes now the S matrix, tells you what S matrix is, which makes sense, because when particles are very separated, you can put any combination of plane waves. But as soon as you require compatibility when they are close, as soon as you impose the Schrodinger equation also when they are close, it tells you how exactly they scatter. So not surprisingly, from the second equation, we fix the S matrix, and what we get is some simple expression, S of P1, P2 is equal to some simple trigonometric function, which is 1/2 cotangent of P1 over 2 minus 1/2 cotangent P2 over 2 plus I over the same thing with minus I. Okay, I think inadvertently I already called it an S matrix, because this constant is exactly what it is. If you have some incoming wave and some outgoing wave, by definition, what multiplies, what tells you what's the probability of getting the out wave given an in wave, is what we call an S matrix. So this is the definition. If you want this object S, by definition of what an S matrix is, this is the definition of the S matrix. Okay? So this is the spin chain S matrix. So this wave function, you can write it schematically as saying that you have one plane wave that doesn't interact, plus a plane wave where there is some S matrix there. What I wrote there is 2, 2, 2. It's a 2, 2, 2 S matrix. Okay, very good. And now you could also, one thing you could also do is also repeat this exercise for higher loops. And you would conclude that then there will be some one loop correction, some corrections to this expression. Okay? If you would study two particles using the higher loop Hamiltonian, they would again also at long distances be just two plane waves with an S matrix by conservation of energy and momenta. It can be nothing else. But when they are closed, the wave function could be modified, and this S matrix will be corrected by considering some corrected interaction. Okay? So we have two objects. So for up to two particles in any one-dimensional system, this is what we have. It's an S matrix between the two particles and the energy of each particle. And this is all there is, because there is a conservation of momentum and energy. Yes?
I feel like I'm missing why they should behave like colliding particles. So I understand the abstract definition of what we're working with, but then why should we expect them to scatter off like particles?
This is just some spin chain Hamiltonian where particles move, right? They move freely with some, where the movement of them is described by these first equations when they are separated, which is just a discrete Laplacian. So it's exactly, this is the discrete version of just a usual Schrodinger equation where you have some kinetic term, d square, right? Some d square of psi, and then some interaction v times psi. So this is just a discrete Schrodinger equation for particles in a spin chain. The particles are these derivatives. They move according to this discrete Laplacian, and then they interact. And the interaction is given by these terms of the Hamiltonian when the derivatives are closed. Okay? In other words, if you have a spin chain, imagine now you have a magnet, you have many, many spin chains. What are your fundamental excitations of your spin chain? It's a spin flip. And the spin flip, you can have some momenta, can move in some momenta. Right? Now if you have two spin flips, imagine really a physical system, then you can, these two momenta can move, and of course they will hit each other and something will happen. Okay, very good. Now there's something missing here, important, something important missing. Can someone try to guess what it is? What have I been missing? What have we been missing if we trace back to the original problem we are interested in? If you remember, we have the problem we are interested in. There's one parameter that doesn't appear here. What are we forgetting? What is P1 and P2? Can it be whatever we want? So that would give a continuous spectrum of plane waves, right? A continuous spectrum. Can we have a continuous spectrum for an Hamiltonian? No, the levels should be discrete. Right? It's a spin chain. It has some spectrum. It has 2 to the L states, and there are 2 to the L energy levels. But how come? I'm writing P1, P2. What fixes P1 and P2? Why are they not continuous? So when do you start quantizing momenta of particles? Sorry? Exactly. So particles, the momenta of particles in nature becomes quantized as soon as you put it in finite volume. As soon as you are in infinite volume, indeed, the spectrum is continuous. So the spectrum of an infinitely long spin chain is continuous. It's okay. But now we don't have an infinitely long spin chain. This picture, remember, it's a trace. So the picture we have, it's actually a periodic spin chain. So it's a ring. Particles are in a ring. And you have these derivatives moving in the ring with some momentum P1 and P2. So this is the picture we have. So because they are in the ring, they should be quantized. And they are quantized by requiring that the wave function is periodic, as we usually quantize a free particle. And here, the same thing. So we write that the wave function is periodic. It means that psi of n1 and n2 should be equal to psi. Our convention for psi is that the arguments are always ordered. Okay? n1 was smaller than n2. So if we want to translate, we should write the following equation. n2, comma, n1 plus L. Okay? Because if we shift n1 by L, now n1 is bigger than n2. Okay? And now if you write this equation and if you plug it there, you have two exponentials. You compare both exponentials and this gives you two equations. And the equations look as follows. You get that e to the I P1 times the length L times S P1, P2 equal to 1, and you get a similar equation for P2, e to the I P2 times the length times S of P2 P1 equal to 1. This is what you get from this equation. Okay? Note, if the theory was free, if the S matrix was just 1, this would be just a quantization for a particle in a circle, e to the IPL equal to 1. What the S matrix is doing is taking into account interactions, right? Without S matrix, it's just quantization of momenta of a free particle in a circle. So how should we depict these pictures? We should think of these pictures. The cartoon is that you have a particle, and you say that if I carry a particle all over the world, the phase of the particle should be trivial. I should get back to the same configuration. So you can think that you have particle 1 and particle 2. But when you take particle 1 all the way around, there is some free propagation phase that gives the P times L. But it goes past particle 2, so there is an S matrix that gives an extra phase shift. And the fact that the total, that taking a particle around gives you back to the same configuration, translates into this equation. Similarly, for particle 2, you are saying that you take particle 2 around, and as particle 2 goes around, it scatters with particle 1, and again, you should go back to the same wave function. Okay? That's a statement. You have many particles. Take one particle, take it all around, take it back to the same position. You should go back to the same configuration, and this translates into these two equations. Okay? So now, the momenta are not free. Now the momenta are quantized according to these equations. Okay? I remind you, in the free case, this just tells you that P is 2 pi n over L, and then it's some integer. Here is some deformation of that solution because of the interaction. And there are still several solutions. But okay, it's a discrete set of solutions. And the discrete set of solutions is in one-to-one correspondence to the fact that you also have different operators you can consider in the gauge theory. Okay? So it's okay that there are several solutions because there are several operators, but it's good. It's discrete, and it's a discrete spectrum as it should be for any closed finite system. For any finite system. Okay? Any question? So now we really exhausted all there is to do with two particles as well. So we did one particle, we did two particles. The next step is three particles. Yes?
So we don't have periodic boundary conditions?
We do, we do. This is
okay, sorry. But then, if we look at the first wave function, psi n, the top board, if we apply periodic boundary conditions to that one?
There?
No, on the left top one. So above the box, psi n is e to the I pi n.
Ah, very good. Okay, so these are the boundary conditions for two particles.
Oh, sorry, yeah.
For two particles. But it's a good point. For one particle, you get that psi of n plus L is equal to psi of n. So you get a much more trivial equation, which is just e to the I p, let me put a 1, p1 times L equal to 1. So this is what you get for a single particle. Just that the moment of the single particle is quantized. This generalizes it for two particles.
So we are saying the particles are actually bosons? Or?
Yes. Yeah. Yes, are bosons. I mean, the derivatives doesn't matter. If you have a derivative here, or two derivatives here, it's of course the same thing.
Because your equation looks like that we are dealing with bosons rather than we have actually. Well, it's both, but.
Yes.
Because you have psi n2 n1, and then you plug n1 plus L is the same as n1.
That's right. Exactly. Exactly. So what David is saying is that one way of thinking about this is the following. You have a wave function that you define for n1 smaller than n2, just not to overcount, just not to write a sum that contains twice the same ket. Right? Alternatively, you can say that the wave function, what's the probability of getting some n1, n2, where n1 is bigger than n2? Well, of course, you just go at the ket and say that this is the same as psi n2, n1. They are there or they are there. Okay? So as soon as, if you define the rule that when you have a wrong ordering, you just flip them, then you don't need this funny flipping that I did here. You can write just psi n1 n2 is psi n1 plus ln2. Okay? You just must be aware that you can only use that expression when n1 is smaller than n2. If n1 is bigger than n2, you flip n1 and n2. Okay? Okay, very good. So now we go. So next, 3 particles. Everything is so clean until now. Let's do 3 particles. Now, I should tell you that in any physical system, what we have done would be roughly the same. Any one-dimensional system is very similar. You have a particle that propagates, 2 particles they can scatter, but then 3 particles, it's always a huge mess. This is always the case. And why is it the case? Because for 3 particles, the naive expectation is that we get some huge mess. And the reason is that P1, if you now have 3 particles with momenta P1, P2, P3, okay, they can go to anything provided the sum P1 plus P2 plus P3, which is the momenta, is fixed, and epsilon of P1 plus epsilon of P2 plus epsilon of P3, which is the energy, is fixed. Okay? It can go to anything, so to any P1 prime, P2 prime, P3 prime, such that this is fixed. But there is a huge phase space. There is still a 1-parameter phase space, so you get typically just a very complicated situation. Okay? This is life. However, it turns out that no. Okay, we do not get a mess. We do not get a mess. Instead, this is what we get if we study the 3-particle interaction. So what would we have to do? Well, what we would have to do is now add a few more lines, 3 or 4 more lines to the Hamiltonian when you now also consider up to 3 derivatives and repeat the same exercise. But you find the following. You find that the wave function for 3 particles is given by what is called there is a nice ansatz for the wave function. Ansatz is something that you try. It's a replacement. You replace something and see if it works or not. And there is a nice ansatz for the wave function that Beta came up with in 31, which is called the Beta ansatz. And it's really a very wise ansatz because it works. It does diagonalize the Hamiltonian. So what is this ansatz? Well, it starts by the naive attempt where you try to write just 3 plane waves. Okay? So you start by just writing P1 and 1, P2 and 2, P3 and 3. So this term, you think of it as 3 particles. But then you go on and say, well, but particle 1 and 2 could scatter. I could have some S of P1 and P2, and then I change P2 and P1. P2 and 1 plus I P1 and 2 plus I P3 and 3. That is, you represent the wave function term that would correspond to this process here. But then you could say, okay, and after this scatter, the guy can scatter 1 more, and then you would write a term which is S of P1, P2 for the first scattering, and then the second one, S of P1, P3, and you exchange P1 and P3 as well. E to the I, P2 and 1 plus I, P3 and 2 plus I, P1 and 3. And you go on, and there are 6 terms you can write. The next one, another one you would write would correspond to this picture, another one to this picture, and the final one to this picture. Okay? So in total, there are 3 factorial terms, which are all the permutations of 3 particles, in the same way that for 2 particles we had 2 factorial terms. This is what you would write if particles were only effectively interacting in a pairwise way. Right? If particles only interacted in pairs by some mechanism, then this would be your natural ansatz. You start with some wave function. And because they effectively only interact in pairs, whenever they interact, they can at most exchange the momenta. And then you don't get a mess, but you get at most a permutation of the initial momenta. Okay? And you remember, so this here, okay, what we see here is that the scattering factorizes. Okay? So it means that we found some hidden symmetry that we could never see at the level of the Lagrangian, say. And that symmetry is integrability. We just found that these particles, they don't interact in a most generic three-particle interaction, but the interactions of three particles factorize into a sequence of two-particle interactions. And this was exactly what we encountered when we started asking, could it be possible, what happens to systems when we have not just momentum and energy, but higher charges? So what we are seeing here is that they just go to a permutation of the original momentum. And this is what you get if you have not only Q1 and Q2, but if you have other higher charges. This was the consequence of having higher charges, that you could shift wave packets by an amount that depends on their momentum. So what we are finding, without constructing them explicitly, is that this theory must have some hidden symmetries, which correspond to hidden charges that we will not guess immediately. Because what we are seeing is that when you consider three particles, all they do is scatter in a factorized way. Okay? Any question here? Well, but as soon as we make this remark, then the picture for n magnons is totally clear. You just consider n factorial permutations.
So how do I know that it's a general solution? So it may solve the equations of motion, but it may be some very special solution that actually solves them, and it's not a general one, so it wouldn't be actually an integrable system.
Right. It could be that you have some system where, say, for 5 particles, there is a solution that factorizes, but it's a very degenerate one, and so on, right? That you could ask. But it's not the case. Let me make a comment in 1 minute about that. Okay, so then what is the picture now for n particles? Let's write what do we have to do for n particles. So again, so then we impose periodicity of the wave function. Now, what will be periodicity of the wave function? Well, periodicity now will tell you that you take a particle, you move it around the circle, it scatters now eventually with many particles, if there is now n particles. This is particle J. And therefore, the kind of equations you expect, the equations you expect are 1 is equal to e to the I pj times L. And then you scatter with everyone else, k not equal to j, s of pj pk. This gives you, quantizes the momenta. This is what you need to solve. This is what are called beta equations. And once you solve them, you compute immediately the energy of your state, which is what? Well, there is some bare energy, which is L plus S, and then some anomalous energy, which is just the sum from 1 up to the number of particles. Let's call the number of particles S, not N, because S is the total number of derivatives, okay? So this S is the number of derivatives, so it's a good number. L plus S plus sum over S of this dispersion that we computed of Pj. Okay? Now, we should stop to appreciate how remarkable this solution is. This is the full solution to the spectrum of a 4-dimensional gauge theory. This gives you the energy levels all you have to do is solve some simple equations with some simple S matrix, compute the values of the momenta, P1, P2, P3, up to Ps, and sum the energy of each of the excitations. Okay? For example, you can try to solve the equations when you put L equal to 2. Right? Okay. At one loop, for L equal to 2, it turns out that there exists a unique solution. Okay? And this is good. We can put here some hoof. And it's good because we know that there's a single primary. So if we started getting more solutions, we'll be in trouble. There is a single solution, and we compute the energy, and we get what? We get S plus 2 plus, indeed, this lambda over 2 pi square harmonic number of S plus tac, tac, tac. Exactly as we expect. Okay? If you want, you can check. For example, it's a simple exercise to take S equal 2, L equal 2, solve these equations, plug into the sum of epsilons, and check that you get what you expect, for example. Okay? So it's very clear. And then you can do L equals 4, L equals 6, and see that it matches exactly what you get. It's really not very complicated. For L equals 6 and so on, you probably have to solve the equations numerically, but for L equals 2, you can solve them analytically, for example. For S equal 2, sorry. For S equal 2. Okay, very good. In general, you can then count solutions of these equations. And you can see that it matches exactly the dimension of the Hilbert space. And this answers David's question. Does it cover completely the Hilbert space? And you can see that it does. It covers exactly for a given fixed S. The number of solutions to this equation matches the dimension of the Hilbert space. So you have a complete base. So then we see that the problem simplified dramatically. So we went, first we had already a huge simplification, which was, so let's summarize what we have achieved. So we started with a 4-dimensional gauge theory, okay, 4-dimensional super Young-Mills. Then we went to the domain of 1-dimensional quantum spin chains. But here, this is still exponentially complex, right? This, if you want to solve it for some big S and L, it's still O plus. And now, we reduce to an integrable model solved by some beta equations, where the complexity is linear. So you can now plug here L equals 10, L equals 100, S equals 20, and solve this in a second in a computer. It will be totally hopeless. It will take like the age of the universe to do the same in any previous approach. But of course, this is, we did not solve the full problem. Keep in mind, we were doing one loop. Okay? But now the problem to compute any dimension of the theory becomes reduced. The problem of computing these dimensions delta is now equivalent to computing epsilon that is as a function of lambda, okay? That starts at lambda epsilon 1 plus lambda square epsilon 2 plus tac, tac, tac. Compute the S matrix as function of lambda that starts at one loop without any lambda plus lambda times the 2-loop S matrix plus tac, tac, tac. And then solve the beta equations. Okay? It's a very well posed problem. Remarkably, it turns out that this dispersion relation, for example, we know it exactly at all loops. And it's actually very simple and quite cute. It's this. It's just this, for example. And if you expand it at weak coupling, you see square root gives 1/2. The ones cancel, and you get lambda over 2 pi squared sine square of p over 2 that we saw today. But this is a no-loop result, and it's obtained by symmetry. It's possible to show by symmetry that this is the case. And this guy, this S matrix, is also known. But that's a bit too messy to write down in the blackboard. If you want more details, I can tell you. It is a correction to this guy. This guy is already a bit too lengthy to write, and now it's a somehow complicated correction to it, but it's totally known explicitly. So to summarize, we have something that we have a four-dimensional super Yang-Mills theory that is described by these quantum spin chains, which are a way of representing these operators. Here I'm considering, say, some spin chain with, and we have 10-dimensional superstring, okay, which are described by some string, which is a one-dimensional object that can have some bumps, some excitation. These spins can move with some momenta p1 and p2. These bumps of the string can move with some momentum p1 and p2, these waves of the string. And the unifying description that describes these two one-dimensional systems, they are unified together in what we can call the AdS CFT integrable model. That, if you want, describes these one-dimensional objects at any value of the finite coupling, and that as you take lambda to 0, it looks like a 1D quantum spin chain. As you take lambda to infinity, it looks like a continuous one-dimensional string. Okay? And it's quite remarkable also to point out that n equals 4 super Yang-Mills, what we are seeing now is that n equals 4 super Yang-Mills, or rather planar, because maybe I didn't emphasize enough, but we are, of course, always considering this limit when n is very large, always implicitly, right? Or this planarity and so on. Planar n equals 4 super Yang-Mills is really a spectacularly special theory. It is conformal. It is supersymmetric. And now we see that it is also integrable. So when we were trying to say, what could simplify a field theory? What could simplify our life? We said that there are three possibilities: conformal theories, supersymmetry, integrability. And we see that secretly, integrability comes in a more fancy way because it comes as an effective description of, in one dimension, of a 4D theory. But we see that in this very kind of intricate way, n equals 4 super Yang-Mills in the planar limit is really what, if you want, the simplest possible quantum field theory. So I think it's fair to say that this is planar n equals 4 super Yang-Mills is the simplest quantum field theory. It is not lambda phi 4, it is n equals 4 super Yang-Mills. And this leads to some hopes. So what would be, just if you are curious, the next to the simplest, people believe, there is actually a paper by Freddy and Nima asking what is the simplest quantum field theory. And the conclusion that they draw is slightly different to the one that I'm advocating, but I think Freddy would subscribe this one as well. That the simplest quantum field theory, the one that wins the contest, is planar n equals 4 super Yang-Mills. The next to the simplest is what is called n equals 8 supergravity. And in third place, it would be n equals 4 super Yang-Mills again, but in the non-planar limit. Non-planar. At finite n. Okay? So if you really have to work at finite n, then indeed, n equals 8 supergravity is probably the simplest quantum field theory. This is what they were advocating. But if we study planar n equals 4 super Yang-Mills, then I think it wins the contest. And what it raises nowadays is the hope that we will be able to solve a four-dimensional gauge theory. And everyone believes that we are very close. There are some quantities that we can already plot. As we said, we will plot tomorrow the cusp anomalous dimension. But there is the claim that very, very soon we'll be able to plot whatever we want in planar n equals 4 superunion mills. Scattering of particles, Wilson loops, dimensions of any operator, 3-point functions of operators, and so on. And there are big hopes for that. No one knows what will happen once that is solved, but I believe it might be like a Pandora box, like when Onsager solved the 2D Ising model. It was also the simplest possible Ising model, but once he solved it, there was an explosion of exactly solvable models, conformal field theory appeared, and it was really crucial to have one solution of the simplest possible quantum field theory. Of course, the Ising model was not very realistic when he was studying it, but it was the simplest one. It was the simplest, and it was really the toy model, the playground for developing new techniques in field theory. And that, I believe, is what we will see with n equals 4. Once we will solve n equals 4 superunion mills, it will be the first example, the simplest one, the prototypal one, and then many others will emerge, and I believe this will lead to a big revolution in physics in general. So I realized that up to 3 particles, I believe it was fairly pedagogical. But then, as we started going here, of course, there are huge gaps. I'm saying that suddenly I go from one loop and I say all loops are known and so on, because now we are moving into a more kind of overview style where tomorrow I will try to give you the broad picture, but necessarily I will not be able to explain all the details, but rather I want at least for you to see what is the result. How does this cusp anomalous dimension look like at any coupling? What's the function? How does it look like? And we should try to plot it. Okay? And for that, we need Mathematica, so tomorrow half of the lecture will be on the computer. Okay. Questions? Yes?
So for the integral, actually got the more conserved quantities. What are they?
Very good question. So what are they? Where is Q3? So now that you know some Q3 exists, you could try to construct it, construct some action. So Q3, okay, this Q3 will be related to some operator Q3, which will be some sum of some action on the spin chain sides that will actually involve 3 particles. Remember that Q3 in the continuous was some PQ, was some slightly more non-local interaction, rather than P squared. Remember, P squared was momenta and Q3 was PQ. And indeed, the analogous statement is that now you start getting slightly non-local interaction with 3 particles. And the claim is that you can construct such charge, Q3, that does commute with Hamiltonian. So such Q3 exists such that the commutator of Q3 with the Hamiltonian is equal to 0. And there is some technology in integrable models that tell you how explicitly can you how exactly can you construct this Hamiltonian.
And then when you jump to that and say that all the higher loops are, I mean, not only for the 3 particles, all the higher together.
Yeah.
So it means you have infinite many of this kind of quantity.
No, actually, as I also emphasized when we were discussing this Q3, if you have Q3 means you can shift packets by amounts that depend on their momentum. So if you have 4 particles that are also going to scatter in the same place, just by shifting them by an amount that depends on the momentum, even just with Q3, you immediately factorize. You see? Because you shift each of the 4 particles by a different amount, so they will already, none of them will already scatter at the same position, you see? Do you agree? Because they have 4 particles, you shift each one by a different amount, they no longer cross at the same point. So, but indeed, but in fact there are more charges. There are many of them. Okay? There are L of them, where L is the length of the spin chain. So you can, it's not needed, but they are there, and you know how to construct them. And just one more comment about the fact that these charges are there. For them to be there, it's absolutely, they are not there at all for a random Hamiltonian. So if you would come here, to your Hamiltonian here, and say, change this 1/2 here and put here some alpha, say, and then try to run to diagonalize this Hamiltonian for a general alpha, everything will break down unless alpha is exactly equal to 1. It will just fall apart like a castle of cards. It's really crucial that it's really, when some Hamiltonian is integral, it's really kind of a miracle that is begging to be described and begging to be understood. And that you could ask, why is n equals 4 integrable? Who gave us this miracle? 4D theories should not be integrable. And the answer would be that because there is AdS CFT, and because strings in AdS 5 times S5 are a very special background, it's a very symmetrical background. AdS 5 times S5 is just a sphere times an hypersphere would hardly be more simple. In the same way that strings in flat space are integrable, I mean the modes of the string are free, they could not be more integrable than free. Modes in AdS5 times S5 are integrable, so if you study the scattering of those modes in the string, they are integrable. And that's something very easy to see. And from that point of view, it's not that special, because string theory is by default a two-dimensional theory. Integrability doesn't come as such a mystery. Then the mystery would be, okay, that's an analysis in classical string theory. Why would integrability be preserved at a quantum level and survive all the way to weak coupling? Right? Which is very, very quantum string. And the reason would be because of supersymmetry, because supersymmetry would preserve these symmetries and make sure they are not broken. So you can say that the fact that we have these miraculous Hamiltonians with coefficients tuned in such that it's integrable, in a sense you can say that this is a reflection of AdS CFT coming all the way from strong coupling, all the way to weak coupling, preserving some symmetry that was there in string theory. Yes?
I didn't understand the definition of a simple quantum field theory. It's only the
No, the simplest quantum field theory is by default the one that will be solved first. But I'm not considering here simplest but interesting. I mean, the same universality class as realistic H theories, not topological theories or something like this. Of course, topological theories are trivial and kind of boring. But and I'm also not discussing two-dimensional theories where conformal group is very powerful and so on. But simplest four-dimensional quantum field theories. It's the harmonic oscillator of the 21st century. I think David Gross coined n equals 4 like that.